Okay. All right. Hey, let's take a look up here. And chapter 8, like I said, I'm not asking you don't have to bring your books every day, but if you do bring your books, hang on. If you don't bring your book, then make sure you're really paying attention here. Because luckily I have a camera, and I can show you everything that's in the book. So, first of all, I show this Ferrari. That's pretty neat. And you say, why is there a picture of Ferrari in a chemistry book? And they're talking about materials. They're talking about things that humans have actually figured out with chemistry. And I don't know if you ever know anybody who owned a Corvette or a Ferrari, but they don't have the same kind of materials that you would have on a Ford 150. You get that, F-150? F-150 would be steel, and they'd make it kind of strong as they could, but they would not try to make it as lightweight as they could. But here, on these kind of race cars, they would try to make the shell, some of them are fiberglass, or the new ones are graphite. Graphite's kind of a carbon thing, and it's really strong, and it's really light. And that makes the car even be able to go even faster. So if you have money for a Ferrari, you know that they spend special money for that material. Now, I'm not here to teach you how to buy a Ferrari, but what I'm going to do is show you this chapter is very mathematical. So we start using mathematics in chemistry, and we'll do that for the next 3 chapters. Now, I don't mean math class. Math class is different. Math class is you do 20 problems, and the teacher grades them, and then you go over another concept and you do 20 problems. And I'm not saying I wouldn't do the same thing as I was a math teacher, but I'm not here to do that. I'm not here to say, let's do 20 problems, let's do 20 problems. We're going to do problems, but they're kind of like story problems in a way. And so we're going to learn I'm going to show you how to do all that today, okay? All right, well, let's start. You're going to hear 2 words during this next chapter, and one of them is a real short word called a mole. So what's a mole? And another fancy word, I didn't learn this word till I got to college, and it's called stoichiometry. So this is like the first of the stoichiometry chapters, because stoichiometry is the mathematics of chemistry. Okay, so everybody ready? All right, so the first part, I'm going to teach you a little bit about the idea of what a mole is, and then I'll show you how to do some of the mathematics with a mole, okay? All right, so again, we're out of the mole, we're out of the lab realm, we're into something else now. All right. Everybody ready? Okay, here we go. All right, take a look right here. They want to teach you an idea. And look at this section here. It says counting by weighing. I don't know if you ever, I know you never thought of, I promise you, you've never thought about this. Think about 1600s, 1700s, early 1800s. They were doing some stuff with chemistry. They mixed this with this, and the alchemists were saying, look what I did. I made this. I made better glass. I made this. Hey, look, when I put these 2 chemicals together, they blew up. They did all kinds of things like that. But the one thing that made chemistry, held it back, was they could never figure out what things were made of. Now, for example, did they have balances that could weigh things accurately? They did. And they knew, for example, that 1 gram of hydrogen would always combine with about 8 grams of oxygen to make about 9 grams of water. So they knew that. They actually knew how many grams of something combined with how many grams of something like that. But they never knew what water was made of. Now, for you, it's like, what, 2nd grade or 1st grade? When did you know what water was made of? You remember somewhere 2nd or 3rd grade, somebody said H2O? Anybody remember that? Now, you would amaze them. If you went back in the late 1700s, early 1800s, you would have been amazed to them. You said, well, that's water. Yeah, it's water, but what's it made of? Well, it's H2O. What? You know that water is made of 2 hydrogen atoms and 1, and by the way, they didn't know what atoms were for a long time. What do you mean H2O? Yes, each water molecule is made of 2 hydrogen atoms and 1 oxygen atom. You're a genius. How did you know that? Here's all I know. I only know what happens when I weigh the materials. Yes or no? Everybody with me? Okay, so, but you understand what chemistry was really wanting to know? They really want to know how many of those atoms combined with how many of those. That was a hard thing to do. So how do we do it? could we shrink ourselves down to the size of atoms and look at it? Hey, look, there's a water molecule. I see. It really is two H's and one O. Hey, can we do that? And that's what amazes me. How did humans figure this out? How did we figure out that water is made of two H's and one O? Right now, you take that for granted, don't you? But in ninth grade, you learned that glucose was C6H12O6, didn't you? How do we know that? How no? We know there were 6 carbons and 12 hydrogens and 6 oxygens. How do we know that? And so the world that we'd like to visit was the world of how many particles are in that. But we couldn't go there. So what's amazing to me? We figured it out anyway. We couldn't visit that world, but we figured it out. And look at this right here. Look at the topic here, 8-1. Counting by weighing. We'll never count atoms in like a drop of water. We won't be able to count how many atoms of gold are in a little piece of gold. We can't count them. Why? They're too small and there's too many. If you started to count anything, you count a million of anything, it would take you a long time. How about a trillion? How about a trillion? It's too many and there's too small. So is there a way to count something without counting it? So what do you think? So what's the thing say? Counting by doing what? Put your book up. Book up. Book up. All right. You think I'm stupid? All right. Give me your phone. Give me your phone. All right. Thank you. All right. So anyway, what we have to do is I'm going to show you a little analogy. So let's turn the page, and I want you to pretend. Okay, we're going to pretend for a minute. I want you to pretend that you own a jelly bean store. You get that? Now, you just opened, and nobody even knows you're open. There are very few people. And somebody comes in and says, well, when did you open this store? I just opened it 5 minutes ago. Well, what do you sell here? Jelly beans. Really? Oh, can I try it? Okay. And so say, well, give me about 10 jelly beans. So now you have this employee that's working for you. You're paying them $10 an hour. And you say, all right. And they go, 1, 2, 3. They count out 10 jelly beans. They ring up the price and give it to them. And that was great. Next customer comes and said, hey, this other person told me he had jelly beans here. Can I get 100 of those? Okay, here's your employee. 1, 2, 3, 4. Okay, it's okay because there's not that many people in the store, is there? And what else was they going to do? They clean up a little bit. But what else are they going to do? Then all of a sudden, after a week, people really have heard about your store, and they come, and all kinds of people are coming. There's like 10 people at a time in the store. And one customer says, I need 1,000 jelly beans. That right there. I like that. It's my favorite flavor. Give me 1,000 of those. Yes? Now what? And more people coming in the store. More people are coming in the store. Now you got 20 people in line. Now they're getting angry. They're getting angry because guess what? They have to wait and wait and wait. And so what are you going to do? If you own the jelly bean store, what are you going to do? You're going to keep doing that? Are you going to count by counting? No, you're not. You're going to figure out something like this. If I owned this store, I wouldn't take 10 jelly beans. What I would do is I would take 500 of them. 500 random jelly beans. I'd weigh them each one. I'd weigh each one at night. I'd weigh them. And look at this right here. This jelly bean was 5.1. Can you guys see the numbers or not? Okay. So I do want you to bring your books. I'm not asking you if you, I'll try to make it bigger if I can. Okay, so one jelly bean is 5.1, and then there's a 5.2 and a 5.0 and a 4.8. So true or false, all jelly beans are identical. That's false. Now, when we look up at the periodic table, I don't know if you remember this from first semester, but hydrogen are like jelly beans. Are all hydrogen atoms identical? No. Some of them have a mass of 1, some of them have a mass of 2, and some have a mass of 3, don't they? That's interesting. So if I were going to do an experiment with hydrogen, how do I know which jelly beans I'm dealing with? You don't. And here, why is this person weighing the jelly beans? So imagine me weighing 500 jelly beans. And then I divide by 500, and I get this number here. This is the average mass of one jelly bean, 5.0111. Now, which jelly bean had that mass? This is important, okay? Which jelly bean had a mass of 5.0111? None of them. This is the average mass. If you get random jelly beans, what's the average mass of a jelly bean? That. Well, guess what I can do now? See my customers? I got 10 people in line, right? I want 100 jelly beans. All right, watch. Give them 501 grams. Scoop. Electronic balance, 501. There you go. What do you want? I want 1,000 jelly beans. Give them 5,111 grams of jelly beans. See? Like that. I never took the time to count those jelly beans, did I? They counted by weighing. Now, if you look up here in the periodic table, what's that decimal number next to hydrogen? I told you there were hydrogen jelly beans, atoms, that have a mass of 1 or 2 or 3. What do you think the average is? What is the average between 1, 2, and 3? 2. Then there should be a 2 up there, but it's not. Why is the average 1.0079? Why is it so close to 1? Anybody? I told you a little bit of thinking involved here, right? Why is the average mass of a hydrogen atom 1.0079? By the way, if I gave you 1 million hydrogen atoms to look at, how many of them would weigh that much right there? None. Some would weigh 1, some would weigh 2, and some would weigh 3, wouldn't it? Why is the average so close to 1? You guys okay today? I'm asking you to think a little bit. Why would the average, what if you took 3 tests and your average was, let's say your average was 90.25. What day did you get a 90.25? You didn't. But what if I know that you got 3 tests and one was a 93, one was an 88, and one was a 90? Wouldn't the average be something around that? So what I'm saying is, what if I told you there were only 2 tests and one of them you got 100, but your average was 80? What's the other one? 60. So you can figure that out, can't you? Look up here, chlorine. I only know of 2 kinds of chlorine. Chlorines that weigh 35 and chlorines that weigh 36. Why is the average 35.5? What do you think that means? How many of each kind of jelly bean? They're about the same, aren't they? There's probably, if you gave me chlorine, about half of them would weigh 35 and about half of them weigh 36. But look at hydrogen. I don't think it's half. The average of 1, 2, and 3 is 2. I don't think there's equal numbers of those, are there? Hey, can I, Sean, do me a favor, okay? Move over here, okay? I can't even see you. Keep going. Keep going. I have to be able to see you, okay? What does it tell me when the average is so close to 1? I keep asking. I can give you the answer, but I'm asking for you to do it.
I don't know.
All right, hey, what do you think? Why would the average be so close to 1 when the average of 1, 2, and 3 is 2? Why is the average not 2? What do you think? What if you had, okay. All right, I'll help you a little bit, okay? Out of 1 million hydrogen atoms, probably 999,990 of them have a mass of 1. And maybe 8 of them have a mass of 2. And maybe a couple of them have a mass of 3. What do you think the average is going to be? Pretty close to 1, isn't it? Because there's so many of them that have a mass of 1. So now, look at this right here. That's what this person is doing. I'm going to be able to count jelly beans by not counting. And that's what that little number is here. That's like the average mass of a hydrogen jelly bean, a hydrogen atom, isn't it? So if I can somehow find out the mass, I can divide it by that and tell you how many atoms there are. All right, so you with me a little bit? So I keep looking at your faces. Either you're really tired or I'm way over your head. Am I way over your head on this? Jelly beans? Okay. So what I'd like to do is I want to show you how to learn this, and then I'll show you how to do the mathematics. All right? So let's take a look right here in your notes. And this right here is what I call the mole concept. So the first thing you do is you have to know what a mole is. All right? And we're going to get there. Now, you'll get tired of me doing this, but I'm going to ask you about what world you're in many times. And the first world I'm going to be in is the little world. Okay, so let's go to the little world and let's take a look at hydrogen. Now again, humans were not ever able to do this, but we figured this out. In the world of hydrogens, if I shrunk myself down to the size of atoms, I'm in the little world now, right? What would I see? If I'm looking at I'm inside a hydrogen balloon, what would I see? And I was like, hey, there's an atom of hydrogen, and I notice it has one proton and one electron. Isn't that right? So here's electrons. This is from the first semester. See if you remember this. Do you remember that? Now, what's the mass of this atom? Remember the grid game? Sean, do you need some paper or pencil? Could you go ahead? I want you to take some notes, okay? I'm not trying to be hard on you, but I don't want to make sure that I want everybody here active today. All right. So what is the mass of one hydrogen atom? And remember, electrons essentially have no mass. Remember that? Remember how 99.99% of the mass of the atom's in the nucleus? And I only have one thing in the nucleus, don't I? So how much is this going to weigh? And one something. And I promise you, an atom does not weigh 1 gram. A paperclip weighs 1 gram. An atom is incredibly small, isn't it? Remember how they made up a new mass unit? What did they call it?
Mole.
No? It was, what was it called? Yes, 1 atomic mass unit. Remember that? And atomic mass unit was somewhere like 10 to the minus 26 grams. So like 0.0000000000000 grams. That's how many grams. Almost nothing. But it was so small, they said, let's just call that 1 AMU. Okay. Now I'm down this little world, and I notice there's another hydrogen atom. So here's a hydrogen. And by the way, how do you write the symbol for this guy? Remember how he wrote the mass number? Remember the mass number? How many, raise your hand if you remember the grid game. You remember playing the grid game and ask what the mass number was? So what's the mass number of this guy? It's right there, isn't it? This is a hydrogen 1 isotope. Let's do another one. Now I'm down here and I'm visiting. Wow, hey, there's another guy. He only has 1 proton also, and he has 1 electron. And, oh wait, what's this other thing? What else is in the nucleus? It's not a proton. What is it? A neutron. Now, how do we write the symbol for this guy? Well, he has 1 proton, so he has to be hydrogen. But what is his mass? This weighs 1, but what about neutrons? They also weigh 1, don't they? So what's his mass? Ooh, this another isotope of hydrogen has a mass of 2, doesn't it? And then there was one more. There was one more. And wow, that's interesting. He had 1 proton and 2 neutrons. And what do we call this one? This was called a hydrogen 3 isotope. So you have hydrogen 1, hydrogen 2, and hydrogen 3. And these are isotopes, aren't there? Now, one more time. Why is the number on the periodic table 1.00797? How many hydrogen atoms have that mass? None of them. But why is the average so close to 1? Why is it so close to 1?
Because there's lots of them.
There's lots of them that are 1, aren't there? Okay, so that's the average mass, and that's called the atomic mass. You okay with this? Now I'm reminding you about things we had in the first semester. If you sit there and act like I don't remember anything, then you're going to have a little more trouble. All right, so anyway, we're in this little world. And we know that the average mass is 1.0079, and that average, this is called the atomic mass. And again, this has a mass of 1 AMU, this has a mass of 2 AMUs, and this has a mass of 3 AMUs. All right, so are you okay in the little world? All right, so let's take you on a little trip, okay? Now I was down there, and I saw 1 hydrogen atom, and it happened to be that 1 hydrogen atom, I put him on a scale. I brought a little balance with me so I could weigh him. And so I weighed him. He happened to weigh 1 AMU. So he must have been this guy here, right? And so how much did the one hydrogen atom weigh? He weighed 1 AMU. Then I went, hey, there's a different kind of atom over there. Hey, that's a carbon atom. He has 6 protons. And I weighed, put him on a scale, and guess what? He didn't weigh 1. Guess what he weighed? Look in the periodic table and take a guess on what this one weighed. What do you think? No, look for carbon. Well, look at the other number. Look at the decimal number. The average is very close to 12, isn't it? Okay, so this one had a mass of 12 AMUs. Well, one thing I found out while I was in this little tiny world, I found out that hydrogen atoms, of course, only have 1 proton. That's why they're number 1. This has 6 protons, but he also had a lot of neutrons, didn't he? And so what I found out was, look at this right here. 1 atom of carbon is 12 times heavier than what? Everybody should be able to finish my sentence, all right? 1 atom of carbon is 12 times heavier than what? Than 1 atom of hydrogen. Now, it sounds so simple, but I'm going to take you on a little trip here. Then I went and gathered 1,000. I got 1,000 hydrogen atoms. And I want to ask you, how much would that weigh? I'm in the little tiny world. Don't say grams now. I'm in the little tiny world. What is it again?
1,000 AMU.
All right. Hey, now I'm hearing some good stuff. Everybody okay? Is that right? And then I went and found 1,000 carbon atoms. How much did that weigh? How much did that weigh? Everybody. 12,000 AMUs. And you know what I found out though? If I had 1,000 of each, this still weighs how much? It's still 12 times heavier. Huh, that's interesting. It doesn't matter. If I have the same number of hydrogen atoms and the same number of carbon atoms, the carbon atoms will always weigh 12 times more than the hydrogen atoms. You know what? I'm going to take the magnification off here so it'll be better for notes. Okay, you okay on that? Now, we'll take you, what if it was 1,000,000? 1,000,000 hydrogen atoms. How much would that weigh? And what about 1,000,000 carbon atoms?
12 million.
Excellent. Now, you're getting close to understanding this. And guess what? As long as you give me equal numbers of each type of atom, what can I always say? The carbons will always weigh what? 12 times more than the hydrogens. Okay, now, I haven't used the word mole yet, but I'm getting ready to. This is going to seem strange to you, but I'm going to pick another number. It's way more than 1,000,000. Matter of fact, it's more than 1,000,000 million. As a matter of fact, it's more than 1,000,000 million. It's more than 1,000,000 billion. It's 6.02 times 10 to the 23rd hydrogen atoms. Okay, now if I gave you that many, that's a lot, by the way. How much would it weigh? See, you get kind of bored there, and now I made a jump. I made a big jump here. What happened here? How much would that many atoms of hydrogen weigh? I bet you know. You had the last answer really fast. So remember, when you're in class, you don't want to just listen. You want to think about it, right? If you thought this was so easy, then why all of a sudden did you hear a roadblock? I'm just going to give you this many atoms. How much does each hydrogen atom weigh?
The same.
How much is that? No. 1 hydrogen atom weighs what? 1 AMU. So if I give this many hydrogen atoms, then how many AMUs would that many hydrogen atoms weigh? That many, wouldn't it? Okay, now you gotta stay with me. Now, it just so happens that if you give me this many. And by the way, I have people every year, they ask me, they'll say something like this: I just don't understand how much a mole is. Okay, can I make it simple for you? If I ask Luke, I got a pair of shoes in there in the room. Does Luke ask me, I just don't understand what you mean by a pair. How many shoes are in there? Why didn't you ask how many a pair was? Because everybody knows it, doesn't it? Hey, Luke, in the other room, there's a dozen baseballs. How many should you find there?
12.
Why didn't he say, I don't understand how many you mean when you say a dozen? Because he knows it, isn't it? I can tell you right now that in chemistry, if somebody says 6.02 times 10 to the 23rd, it is a mole. It is 1 mole. And don't ever ask me then, don't ever say to me, I just don't understand how many a mole is. It's this many. It's always this many. If a dozen's always 12, then a mole's always this many. You get it? You give me that many donuts, you gave me a mole of donuts. It'd be bigger than the planet. A mole is so many, it's bigger than the planet. I can't give you a mole. Even if I gave you a mole of sand grains, it'd be a lot. It's a huge amount. Yes?
So that would equal 1 mole, right?
Yes.
And then for carbon, would you not have to write the...
I have to give you the same number of particles, don't I?
Yeah, but wouldn't you just put 12 moles?
Of carbon atoms. All right, thank you. Now, you can put this in your calculator, but if anybody wants to multiply 6.02 times 10 to the 23rd times what? This was that times 1, isn't it? What's this one have to be multiplied by?
Times 12.
Yes. See, you do understand. Hey, you get this. Now, I'm not going to multiply that out, but you know what? That's a lot of AMUs also, and that's a mole of carbon atoms. Now, here's the key. This is it. This is like the best sentence all day. When you give me this many atoms of hydrogen, this many AMUs, watch now, it's so many AMUs, it also equals 1 gram. Now, that was the breaking point. And guess what this is going to be? I'll give you a hint. It better be 12 times heavier. Now, everybody with me? Here we go, one more time. When you look at the periodic table, I would say if you go to college and you take chemistry, I'll bet a lot of your former students, I'll bet a lot of your colleagues or your peers, they may have remembered something about the periodic table, maybe. But now I want you to look at this regular time and see where it says hydrogen at 1.0079, okay? On the average, let's talk about 1, okay? If I gave you that many grams of hydrogen, and this right here is the big world. You know how I know it's big world? Because I gave you so many that you're now in the world that I can do experiments with. See, I can go with that balance over there. Do you think I could weigh out 12 grams? A paperclip's 1 gram, isn't it? A little paperclip's 1 gram. Could I weigh out 12 grams of carbon? Yeah. And if I put that little black pile right there, that black pile of carbon right there, what would be in my hand? Well, that's 12 grams of carbon. What else is in my hand? How else can you tell me I have it? Well, it's a whole lot of AMUs. What else are you going to tell me? It's 6.02 times 10 to the 23rd atoms of carbon. How did you know that? How did you know that? Did you count that? I didn't have to count it. I counted it by weighing it. If I have 12 grams of carbon in my hand, I have 1 mole, which is also known as 6.02 times 10 to the 23rd atoms. Is that remarkable to me? It's not remarkable to you because I've actually studied this. But I now know how many atoms of carbon are in my hand. If I do an experiment, I can actually figure out how many atoms of carbon react with how many atoms of something else. And I never have to count them. Did I lose you on this? Is that too much? Okay, so let me ask you another question. What if I show you something like this? All right, what does that mean to you? And I'm gonna go 2 different worlds now, okay? This right here could be in the little tiny world where I actually could see the atoms. And what would I say that is right there? That could be one what? What do you call that? Is that right? Is that one molecule of water?
Yeah.
Okay. But what else could H2O stand for? And that's what's interesting about the mole concept. Whatever's happening in the little world, you can magnify it in the gram world. Whatever's happening in the gram world can be demagnified down here. So this represents two things. Okay, I lost you. Hang on. Let's go to carbon up here. See where it says 12 for carbon? What does that number mean? It means two things. It means one atom of carbon in a little tiny world. One atom weighs about 12 what? Please don't say grams. One atom would weigh how much? One carbon atom, how much? I got 12 what? AMUs. You are right. But what if I gave you a whole lot of carbon atoms, like 6.02 times 10 to the 23rd? Now what does that 12 mean? Yes. 1 mole of carbon would weigh how much? 1 atom of carbon is 12 AMUs. What about 1 mole of carbon? 12 grams. Are you with me? All right, look at this right here. In the little world, this means 1 molecule of water. But you know what else could it mean? It could mean 1 mole of water. Now, which one is more water? Which one represents more water? This is just 1 little molecule of water. What does this represent? How many waters is it? Wow. And that's okay. This could mean 1 mole of water or 1 molecule of water. All right. So now what I'm going to do is, do you remember how we did factor label in the first semester? Remember doing factor label? Okay. So what we're going to do is we're going to do a couple factor label problems. And I want to be honest with you. Oh, it's noisy. Okay. I'll tell you what, we may not get to the problems yet, but can you look up here? In order to do factor label, I don't know if you remember factor label, how we changed donuts to, again. What we're going to do is, the key to factor label is having a bunch of things that are equal to each other. So what we're going to do is, we're going to talk about who equals what. All right, so here we go. What if you are an element on the periodic table? All right, so what if you're an element on the periodic table? What can I say about that? Let's pick, you want to do carbon? Which element do you want to do? Anybody have a favorite? All right, let's do carbon. Okay, 1 mole of carbon equals, and how many would that be? How many is a mole of anything? It's not 12. What is it? Now, here's important. What do I put after that? That's very, very important. What's the smallest piece of carbon that still acts like carbon? What would you call the smallest piece you could think of carbon that still acts like carbon? I'll give you a clue. Don't say AMUs. What is it? Yes. Everybody got that? A mole of carbon would be this many atoms of carbon, right? And then, one more, watch now. I go to the periodic table, and a mole of carbon would weigh how much? Now, a mole's a lot, so we're not going to be using AMUs. 12, somebody said it. Yes. 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 Now, if you'll do one more, you'll be done here. If you'll do one more element, okay? So, Riley, pick any, what's your favorite element besides carbon? Pick a weird one then. Bromine. Okay, ready? 1 mole of bromine equals, go ahead, finish my notes for me. You do it. Finish my notes. Here, you write it before me, okay? 1 mole of bromine is what? What are you going to put after that? And now, go to the periodic table. Go to the periodic table. 79.9. What do you think? What do you think? Is that working for you or not? Okay, now I'm going to show you how powerful this is. Let's do an example problem. It'll take us about less than a minute. All right, I'm going to make one up, right? Let's see. How about, I don't know, 20 grams of bromine equals how many atoms? All right, let's talk about factor label, okay? Ready? We're going to do a lot of factor labeling here. What was always step 1 in factor label? Always. Write the given. 20 grams of bromine. That's my given, isn't it? Here we go. Now, step 2 was to multiply the given times a conversion factor. Now, this is important. Where do you get the stuff to build a conversion factor? And you get them from what? Equivalents. Now, watch now. I have 3 equivalents for bromine, but I can only use 2 of them. How do you know which 2 to use? Here we go. What label up here has to go away? And how do you get grams of bromine up here to go away? You put it there. Don't they cancel? And what label would you like to replace it with? All right, in 10 more seconds, we're going to be done. Tell me what numbers go here. Look up here.
6.02 times 20.
For which one, though?
Bottom.
Why?
Top, my bad.
This goes with atoms, doesn't it? So if I see atoms, I'm going to do what? Now, what number goes with grams? No. No. There you are. There you are. Okay, so tonight, you don't have to turn it in, but how do we finish this problem? This times this divided by that. All right, thank you very much.